Welcome to the Agile Software Engineering Deep Dive, the podcast where we unpack the ideas shaping modern software engineering, technology, and leadership. My name is Alessandro Guida, and I've spent most of my career building and leading software engineering teams across different industries. Today, I want to take a small field trip into software engineering memory lane. Software engineering has changed dramatically. We have better languages, better frameworks, better pipelines, better automation, better cloud platforms, and now AI assistants that can help us write, explain, and review code. But in the middle of all this progress, I sometimes wonder whether we have also forgotten a few useful engineering disciplines. Not because the past was better, it was not. But some older practices were built around questions that are still very relevant. Are we stabilizing? Does done really mean done? Are known defects visible? Do we understand what our bugs are trying to teach us? Do we know what must never break silently? Are users actually able to use what we have built? And do we detect performance degradation before it becomes failure? In this episode, we revisit a few forgotten or half-forgotten practices. Zero bug bounce, zero bug strategy, definition of done, entry and exit criteria, code freeze, bug triage, root cause analysis, regression testing, usability lab testing, and performance testing. The point is not to bring back old bureaucracy. The point is to remember the engineering discipline that was hidden inside it. So let's dive in.
We're currently surrounded by AI coding assistants and lightning-fast cloud frameworks and these massive automated pipelines.
From absolutely everywhere.
Right, and yet modern software teams are continually shipping products that just quietly break under the surface.
Yeah, they really are.
Why is that? Well, because in our relentless rush to adopt all the shiny new tools, we might have accidentally thrown away the grandfather's hand tools of software engineering.
Which is a huge problem.
It is. So, welcome to today's Deep Dive. I'm your host, and our mission today is to explore issue 36 of the Agile Software Engineering newsletter.
The one titled A Field Trip into Software Engineering Memory Lane.
That's the one. It's a vital read for anyone building systems today because the sheer pace of modern development has created this massive blind spot regarding fundamental engineering discipline.
It really has.
I look at this deep dive kind of like cleaning out a grandfather's workshop.
Oh, I like that analogy.
Yeah, so you walk in, and at first you might laugh at some of the heavy, dusty old machines in the corner, you know?
Like the massive iron presses and stuff?
Exactly. The belt-driven lathes, they just seem so slow and outdated compared to, like, a modern 3D printer.
Right.
But then you open this weathered wooden drawer and find a set of hand tools. You pick them up and you realize these chisels and planes are sharper, better balanced, and honestly more precise than anything you can just buy with a click on Amazon today.
Yeah, and that's exactly what we're looking for in this source material, those perfectly balanced hand tools.
Right.
Because what's fascinating here is that the author is incredibly careful not to romanticize the past.
Oh, for sure.
We are absolutely not saying the quote-unquote good old days were perfect.
Right, because they weren't.
No, they weren't.
Yeah.
I mean, waiting 6 months for a release cycle was just agonizing.
Brutal.
And the heavyweight, endless documentation phases were completely suffocating for developers.
Yeah, nobody wants to go back to that.
Exactly. So we are not looking for nostalgia. We are looking to extract the timeless engineering discipline that was baked into those older practices.
Mm.
We want to separate the underlying logic from the outdated bureaucracy.
That's the goal. And before we start unpacking those specific tools, just a quick bit of housekeeping for you listening.
Always important.
Yeah. While this deep dive is completely free, it is a massive help to us if you press like on this platform and subscribe to receive all our future deep dives.
It really does help out a lot.
It does, but
Yeah.
honestly, more importantly, you need to go read and subscribe to the full original newsletter article.
Absolutely.
Because we are covering the overarching architecture of these ideas today, but the original text contains these essential visual blueprints.
Yeah, the flowcharts and illustrations.
Right. Illustrations of these engineering concepts that are they're impossible to fully capture in an audio format. You really need those visuals to see how all the pieces fit together.
The illustrations absolutely anchor the theory into everyday practice. Highly, highly recommended.
Okay, so let's establish our foundation. If we want to understand how to build resilient software, The source argues we first have to agree on a quality baseline.
Right, the absolute basics.
Yeah, before we even talk about deployment pipelines, we have to define what a bug actually is and what finished means.
Which introduces a metric that, I have to say, sounds like it belongs in the early 2000s.
Oh, you mean zero bug bounce?
Yeah, it really does have a retro ring to it.
It does.
But its function is completely relevant today. I mean, instead of just looking at a static dashboard that says, we have 40 open bugs.
Right, which doesn't tell you much.
Exactly. Zero bug bounce looks at the behavioral trend of the system. So as you approach a release, are the defect counts steadily moving towards zero, or are they bouncing?
Bouncing meaning what?
Ascending. The count falls to 30, then suddenly spikes to 45, then it falls to 20 and jumps to 35.
Oh, I see. So it's diagnosing the difference between actual stabilization and just playing defect whack-a-mole.
Yes, that's a great way to put it.
If the count is bouncing, it tells me that our developers are fixing one thing. But because the architecture is, I don't know, fragile or tightly coupled,
Right.
that fix inadvertently breaks two other things elsewhere.
Precisely. And fast CI/CD pipelines can actually mask this problem entirely.
Oh, really? How so?
Well, they give a team the comforting illusion of progress because things are moving so quickly. Code is merging. Tests are passing in isolation.
Ah, right.
But that movement isn't stabilization. The bounce is the system's way of telling you that you have a structural problem, not just a localized code problem.
Which naturally brings us to another foundational concept the author brings up, which is the zero bug strategy.
Yes, the make it clean, keep it clean philosophy.
Right. And the source makes a pretty stark observation here. It points out that new features, well, they have sponsors.
Oh, definitely.
They have deadlines, roadmaps, and you've got executives actively asking about them in board meetings.
Constantly.
But bugs, on the other hand, only have users.
It's a really harsh reality. I mean, if a bug is simply dropped into a flat, massive product backlog right alongside shiny new features,
Yeah.
it will lose that prioritization battle almost every single time.
See, I want to push back a little on the framing of a zero bug goal, though.
Okay, let's hear it.
Because it sounds incredibly naive on the surface. Like, complex systems fail, network latency fluctuates, users do entirely unpredictable things, and edge cases hide everywhere.
Right, of course.
So building perfectly flawless software is a myth.
And the source actually agrees with you.
Oh, it does?
Yeah. A zero-bug strategy does not mean pretending the software is flawless or that zero defects exist out in the wild.
Okay, and then what does it mean?
It's an active management philosophy. It means when a defect is discovered, you don't just quietly normalize it. You make a binary choice.
Which is?
You either fix it immediately or you make a conscious, documented decision to accept that specific risk based on business value.
Oh, I see.
What you never do is let bugs become invisible quality debt that acts as, like, permanent furniture in your backlog.
Okay, so it's the difference between acknowledging a small leak in the roof and deciding, it's not worth fixing until summer,
Right.
versus just putting a bucket under the leak, walking away, and eventually completely forgetting the bucket is even there until the floor rots.
That is the exact mechanism of quality debt.
Yeah.
And it ties directly into how a team defines the finish line.
The definition of done.
Exactly. We have to talk about that.
Ah, yes. It is almost done. Probably the most dangerous phrase in an engineering stand-up.
Completely. Because almost done usually means the easy part is finished and the actual complex integration work hasn't even started.
Yeah, I've been there.
Right. In many modern workflows, done has devolved into a mindless checklist. The code is written, a peer approved the pull request, and it merged to the main branch.
Boom. Leave the ticket to the done column.
Exactly. But the original discipline of done wasn't just a project management status. It was a rigorous engineering fitness test.
Okay, unpack that a bit.
It asks if this piece of code is actually fit to be grafted onto the living organism of the product. It forces the developer to ask real questions.
Like what?
Like, did I consider the security implications? Can the operations team actually monitor this feature when it's live? Have we given customer support the documentation they need to handle the inevitable user questions?
Right. So the definition of done forces the team to confirm that the product is genuinely better, not just larger.
Exactly.
So once a team establishes that solid quality baseline and truly understands what done means, a new problem emerges.
Oh, control.
Yes. How do we control the flow of all this work rushing toward that finish line? Because without flow controls, a fast pipeline just delivers chaos, but at a higher velocity.
Right, which helps no one.
Exactly. And the newsletter addresses this with entry and exit criteria.
Now, to a modern team, entry and exit criteria sounds like heavyweight waterfall bureaucracy.
It sounds like endless committee meetings, honestly.
It really does. But if you strip away all that corporate baggage, it is simply a mechanism to ask two vital questions.
Okay.
Entry criteria asks, are we genuinely ready to start this work? And exit criteria asks, is it safe to move this work to the next stage?
I always think of it like a bouncer at a busy nightclub.
Oh, it's a good one.
Yeah, the bouncer essentially manages capacity and safety, right? So entry criteria is the rope outside. You don't let a group of people in if the club is already over capacity or if they don't have their IDs ready.
Right, you have to be prepared to receive them.
Exactly. And then exit criteria is the bouncer at the door checking people leaving. You don't let someone get behind the wheel of a car if they are visibly intoxicated.
Yeah, it makes sense.
It's not about slowing down the fun. It's about preventing a disaster.
It's a very fitting analogy. Because if an engineering team bypasses the entry bouncer, say, they start coding a feature before the database schema is actually finalized.
Or the API isn't ready.
Right. They end up building against a ghost dependency. And that basically guarantees a massive loop of rework and waiting times later on.
Total nightmare.
It is. In highly complex systems, particularly those involving physical hardware or, say, medical devices, enforcing strict exit criteria prevents wishful thinking from pushing a half-baked component downstream.
Now, speaking of controls that modern developers absolutely recoil at, let's talk about code freeze.
Oh, boy.
Right. In the era of continuous deployment where teams deploy to production 10 times a day, code freeze is treated like a dirty word.
And historically, it earned that bad reputation.
Did it?
Oh, yeah. A code freeze used to be a symptom of severe dysfunction. Teams would build in this chaotic free-for-all for 6 months, integrate it all at the very end, realize absolutely nothing worked in.
Oh, yikes.
And then scream freeze.
Oh, yeah.
So they could spend a month desperately patching a broken monolith.
Right, that sounds awful. But the newsletter kind of reclaims the concept, doesn't it?
It does.
It argues that a code freeze shouldn't be a panic room you hide in because your daily process is broken.
Right. For certain environments, think enterprise platforms or railway routing software or systems deeply integrated with custom hardware. A code freeze is a deliberate, highly disciplined stabilization window.
Okay, a stabilization window.
Yeah. Its purpose is to protect the release candidate from unnecessary late-stage changes while the team actively collects evidence that the system performs safely under load. It's a strategic pause, not a reaction to failure.
Got it. But even with disciplined flow controls and the bouncers at the door and those stabilization windows, the reality is that bugs will still escape.
They always do.
They will slip through into production. And the source makes a pretty compelling argument that how a team reacts to an escaped bug really separates a mature engineering culture from an amateur one.
And that reaction has to begin with bug triage.
Right.
Today, triage is often just a fancy medical term for backlog grooming. We assign a severity label, estimate the story points, and shuffle the ticket around the JIRA board.
Guilty as charged.
Right. But true triage is an investigative process. It asks, is this isolated, or is this smoke from a larger systemic fire?
Which flows right into defect escape analysis. And the author has this brilliant framing for this.
Yeah, I love this part.
They say fixing a bug simply repairs the product, but root cause analysis repairs the engineering system.
That is the core distinction. When a critical defect escapes into the hands of the user, a mature team stops and asks, where exactly should our net have caught this?
Right. Like, was the unit test mocking too much data so it missed a real-world edge case?
Exactly. Or did the peer review gloss over it because the pull request was just way too large?
Oh, that happens all the time.
It does. And this isn't about blaming the developer who wrote the code. Blame destroys psychological safety and hides the truth.
Right.
This is about discovering how the system allowed the defect to walk right out the front door unchecked.
Okay, let me formulate a hypothesis here because I can just hear modern teams arguing against this.
Okay, bring it on.
If a team has a massive, highly automated CI/CD pipeline, we are talking thousands of automated tests running on every single code commit. Don't they fundamentally bypass the need for traditional regression testing?
I see where you're going.
Like, isn't the pipeline the safety net?
Well, if we connect this to the bigger picture, we see the flaw in that logic pretty quickly. A massive pile of automated texts is merely an execution engine. It is not a regression strategy.
Because the automation just blindly executes whatever it's told.
Exactly.
It doesn't inherently know if it's testing the right things.
Exactly. Automated tests are remarkably fast, but they are completely devoid of business context. A true regression strategy requires human engineers to sit down, look at the architecture,
Yeah.
and ask a very deliberate question.
Which is,
What must never break silently?
man, that shifts the entire perspective. It moves the burden of responsibility from the automated machine back to the engineer's judgment.
It forces the team to identify the critical user journeys, the core security authentications, the financial transaction flows. If your fast pipeline is executing 10,000 tests, but it lacks coverage on the one data migration flow that absolutely cannot fail well, you haven't modernized your quality discipline. You've just automated your blind spots.
That is a crucial distinction. And it provides the perfect pivot to one of the most vital chapters in this deep dive.
Yes, let's get into it.
Because up until now, we've been talking about functional breaks, like when the system throws a glaring error, crashes, or returns the wrong data.
The obvious stuff.
Right. But what happens when the system still technically works, but it is quietly dying under the surface? I really want to spend some time unpacking performance testing here.
This is critical, and we need to clarify our terms immediately.
Okay.
We're not talking about the monolithic end-of-project load tests from 20 years ago.
Right, where a specialized siloed team took 3 weeks to script virtual users just to see if the server would catch fire.
Exactly, not that.
Yeah. The modern, lightweight approach the author champions here is completely different. I liken it to checking your blood pressure daily.
Oh, that's a perfect analogy.
You aren't scheduling a full surgical workup or an MRI. You just use a simple cuff every morning to take a quick measurement. The value isn't in any single day's number. The value is in spotting a dangerous upward trend long before you actually suffer a heart attack.
That's the exact mechanism. The source details how modern teams can utilize their existing, everyday automated test cases and simply attach expert telemetry markers to them.
Okay, so how does that work?
Well, when the test runs, you don't just ask, did it pass? You measure the execution time. You measure the memory consumption. You count the exact number of database calls it took to render the page.
Oh, wow.
Yeah, and it requires very little overhead to actually capture this data.
So if I have a functional test for a user login, I'm now also tracking that it took, say, 200 milliseconds and used 15 megabytes of memory.
Exactly.
But a binary pass-fail test completely ignores that data. If tomorrow the same login takes 210 milliseconds, the functional test still glows green. Everything looks fine.
And this raises an important question. At what point does a system that is gradually slowing down become a system that is actively unsafe?
That's a great question.
Because a system rarely just snaps and breaks out of nowhere. It degrades.
Right.
Yesterday's perfectly acceptable code becomes slightly slower today because someone added a nested loop. And then it gets slightly slower tomorrow because a new database index is missing.
And the newsletter captures this phenomenon with a brilliant observation. It notes that software has this remarkable sense of theater.
Oh, it really does.
It never fails on a quiet Tuesday afternoon. It fails at the absolute worst possible moment.
It fails on Black Friday. It fails during the Super Bowl ad.
Yep.
It fails the exact moment the CEO logs in to do a live demo for investors.
Always.
And why?
Yeah.
Because that gradual 10-millisecond degradation you ignored suddenly compounds when 1,000 users hit the system simultaneously. It exhausts connection pools. It creates these invisible queues.
This is honestly the most powerful takeaway from this chapter for me. A slower response time is almost always the very first warning sign of a future crash.
Absolutely.
It is the system whispering to you that it is struggling under the weight of its own architecture. And if you aren't actively tracking those lightweight performance trends, if you aren't checking the system's blood pressure, you will never hear the whisper. You will only hear the scream when the servers go down.
And the engineering return on investment for catching that whisper is just immense.
Oh, I bet.
You optimize the database query or fix the memory leak on a random Wednesday long before the users ever experience friction and long before the operations team is paged at 3:00 a.m.
Okay, let's map out the ultimate scenario. Let's say a team has implemented everything we've talked about.
Okay.
They have perfect flow controls. Their defect escape analysis is flawless. The system's performance is lightning fast, and their regression suite guarantees absolutely nothing breaks silently.
Sounds like a dream team.
Right. Technically speaking, they have engineered an absolute masterpiece. But what if a real user logs in, stares at the perfectly functioning interface, and has absolutely no idea how to accomplish their task?
Then the software is not finished and the engineering has failed.
Boom. Which brings us to our final major focus today, moderated usability testing.
Yes.
Now, I know there are engineers listening who might instinctively push back here thinking, usability, user confusion. That is the UX design team's problem. My job is to make sure the data saves correctly.
And the author fundamentally rejects that boundary.
Totally.
Building a system that technically executes but cannot be intuitively operated by its intended human user is a failure of the entire product team, engineering included.
Here's where it gets really interesting for me because of how modern teams try to solve this problem.
Right, with the analytics.
Yeah. If a team today wants to understand user behavior, they almost exclusively turn to analytics. They run massive A/B tests. They look at heat maps of where the mouse goes. They track click-through rates on dashboards.
Data.
Exactly. And I would assume that with 50,000 recorded user sessions, the data would clearly show us exactly where the user experience is failing.
It shows you that it failed.
Yeah.
It does not show you why it's failed.
Well, that's a good point.
And that is the crucial limitation of purely analytical data. Analytics will tell you exactly where on the page the user abandoned the process. Moderated usability testing tells you the human reasoning behind the abandonment.
Okay, but how does it actually extract that reasoning? Are they just like interviewing the user after the fact?
No, because human memory is flawed, and users often try to retroactively justify their confusion to sound smarter.
That makes sense.
The source highlights a very specific, deeply revealing method called the Think Aloud protocol.
The Think Aloud protocol.
Yes. You put a real user in a lab setting, virtual or physical. Give them a realistic task to complete on the software, and instruct them to simply narrate their inner monologue in real time as they navigate.
So they aren't defending their choices, they're just vocalizing their immediate expectations. Saying things like, okay, I've entered my payment info. I expect the confirmation button to be at the bottom right. Wait, it's not there. I'm scrolling up. I don't understand what this error message means. Does exception 404 mean my card was declined?
Yes. And as an engineer, watching a real human being genuinely struggle to use the feature you just spent 3 weeks building is an incredibly vulnerable, humbling experience.
Oh, I can only imagine.
The analytics dashboard cannot show you the 5 seconds of anxious hesitation before a user clicks the wrong button.
Wow.
Right? A heat map doesn't explain that the user completely ignored your primary call to action because it looked too much like an advertisement.
Oh, banner blindness.
Exactly, banner blindness.
That really shatters the ultimate engineering illusion. The belief that if the feature functions correctly under the hood, the user experience is inherently successful.
It is a dangerous illusion. A feature can boast 100% unit test coverage, execute in 5 milliseconds, be technically flawless in its code, and still completely fail the human test.
And the source makes a pretty bold, quantifiable claim here. It says watching just 5 users employ the Think Aloud protocol and stumble in the exact same spot will teach an engineering team infinitely more about their product's quality than analyzing a dashboard with 50,000 raw events.
Absolutely.
You cannot just measure your users like they are server nodes. You have to watch them, and you have to listen to their confusion.
Because aggregate data inherently lacks empathy. Data shows you the cold behavioral outcome after the fact. But watching someone think aloud pulls you directly into their subjective experience in the moment. It reveals the exact gap between the engineer's mental model and the user's reality.
So what does this all mean for us today? We've looked at the bouncer, guarding the flow of work, the daily blood pressure checks of performance testing, the humility of listening to a user think aloud in the usability lab.
We've covered a lot of ground.
We have. And as we wrap up this deep dive, I think the most powerful takeaway for you listening is that while the syntax and the tool chains have drastically evolved, and thankfully, we've left the suffocating bureaucracy behind, the core engineering questions remain completely timeless.
They endure because human complexity hasn't changed. Are we actually stabilizing the system or just thrashing? Is it genuinely safe to move this code forward? Have we decided what must never break silently?
They really are the grandfather's hand tools. They might look a bit dusty at first glance, but they cut cleaner and build stronger foundations than anything else.
Oh, good.
Before we sign off, one final reminder. Please take a second to hit like and subscribe to this channel to catch all our future deep dives. And crucially, go read issue 36 of the Agile Software Engineering newsletter. Subscribe to it. You really need to see those visual blueprints and explore the full depth of the author's arguments that we couldn't fit into our time together today.
And to leave you with one final thought to mull over.
Go for it.
We've spent this entire deep dive discussing practices that fundamentally rely on human intuition and judgment. The wisdom to ask why a bug escaped our net. the strategic foresight to decide what must never break silently, the empathy required to listen to a user express confusion and realize our design failed them.
Right.
As we increasingly hand the keys over to AI, relying on it to write our code, generate our test suites, and autonomously review our pull requests, what happens to the actual quality of our software?
Oh, wow.
If the machine is doing the building, will we eventually lose the engineering muscle memory required to even know what questions to ask when the system silently begins to fail?
Man, a heavy, essential question from the workshop. Thanks for joining us on this deep dive. Catch you next time.
Thank you for listening to the Agile Engineering Deep Dive podcast. If you found this episode valuable, feel free to share it with someone who might benefit, a colleague, your team, or your network. You can access all episodes by subscribing to the podcast and find their written counterparts in the Agile Software Engineering newsletter on LinkedIn. And if you have thoughts, ideas, or stories from your own engineering journey, I'd love to hear from you. Your input helps shape what we explore next. Thanks again for tuning in, and see you in the next episode.